Hello friends, welcome to another chemistry video from eLearn. My name is T-Man and I'm a chemistry tutor at eLearn. In this video, we'll discuss electrolysis of aqueous ionic compounds, that is ionic compounds dissolved in water. Let's first answer the question, what is electrolysis? Electrolysis is the decomposition of an ionic compound when molten or in aqueous solution by passage of an electric current. Now, electrolysis is a decomposition reaction just like thermal decomposition and photolysis. You remember that for thermal decomposition, you need heat to break down a compound. And for photolysis, light is required to break down the compound. For electrolysis, we use direct current, that is the form of electricity supplied by batteries and cells to break down the chemical substance. Now, we are going to start by looking at an electrolytic cell. An electrolytic cell will look like this. It has three components. Number one, we have the battery, which acts as the DC source, supplies the energy required to break down the ionic compound. Number two, we need electrodes. Now, electrodes are pieces of metal that conduct electricity or an electric current into the electrolyte. So we have two types. The first one is called the anode. The anode is connected to the positive plate of the battery, which means it's positively charged. And then we have what is called the cathode, which is connected to the negative plate of the battery, which means it is negatively charged. Third, we have the electrolyte, which is the ionic compound that is being electrolyzed. We are breaking it down into its components. Now, when it comes to electrolysis, the electrolyte contains free ions. These are the ones that are responsible for conducting electricity in the system. And then we also have electrons that conduct electricity in the external circuit. Now let's look at the anode. There is an electron there. Now the electron moves from the anode to the cathode. When you want to look at the process, we can think of the battery as a means to pump electrons from the anode to the cathode. Now let's look at the electrolyte in more detail. Any molten or aqueous substance that conducts electricity and is decomposed by it. So when you look at a metal conducts electricity, but a metal is not an electrolyte because it is not decomposed by the electricity. So ionic compounds, when they are molten or aqueous, do the two things. They conduct electricity and are decomposed by it. Now, the molten or aqueous ionic compounds have free ions that can move when we apply a potential difference. When we connect the system to a battery, the ions are free to move. Solid ionic compounds cannot conduct electricity because the ions cannot move. Therefore, solid ionic compounds cannot be used as electrolytes. When we look at water, water is considered a weak electrolyte because it partially dissociates into ions. This means that whenever you have water, there are free ions present, and these ions can conduct electricity. Therefore, water can be considered an electrolyte. Remember, water is a covalent compound, but because it ionizes, it is an electrolyte. Now, let's look at the electrodes in more detail. An electrode is any electrical conductor that is used during electrolysis to convey electricity into and out of the electrolyte. Now, what this means is that you have one side that allows electrons to flow out of the electrolyte and one side that allows electrons to flow into the electrolyte. Now, your electrodes can be inert, which means they do not react, number one, with the electrolyte, number two, with the electrolysis products, and number three, do not dissolve in the electrolyte. And we also have electrodes that are reactive. We are going to look at these in more detail. As we have discussed before, we have an anode, which is connected to the positive side of the battery and is therefore positively charged. And then we have the cathode that is connected to the negative side of the battery and is negatively charged. Okay, now let's go into detail and look at the electrolysis of aqueous ionic compounds. Now, when you have an aqueous ionic compound, this substance is going to consist of the metal ions coming from the compound and H+ ions that are coming from water. You also have the non-metal ions coming from the compound and OH- ions that are coming from the water. Now, during electrolysis, the cations move to the cathode where hydrogen or the metal is formed. And then you have the anions that are going to move to the anode where oxygen is going to be formed together with water or the non-metal. Next up, what we need to understand is that there is going to be competition at each electrode. As we have seen, at the cathode, we have hydrogen ions and the metal ions coming from the compound. Which one is going to be discharged? It's competition. And when you go to the anode, you have the non-metal ions and the hydroxide ions. Which one is going to be discharged? There is going to be competition. Now, the ion that is discharged in this process depends on two things. Number one, there is the relative concentration of ions. As a rule of thumb, the ion that is present in greater concentration is preferentially discharged. Number two, we have the relative reactivity. Now, when we come to relative reactivity, we use the reactivity series of metals to decide which ion is discharged. Now, if you remember your reactivity series of metals, and we look at the examples as given here, potassium is the most reactive metal. This means that potassium has the least reactive ion. So ease of discharge in this example increases down the series. Ag+ is the one that is more reactive or most reactive, and potassium is the one that is least reactive. As a general rule, we say that potassium ions, sodium ions, and calcium ions are never discharged from an aqueous solution. Now, when we go to the anions, we also have another series. This one you will have to memorize. But for purposes of IGCSE or O Level chemistry, the ones that we focus on are the chloride, the bromide, the iodide, and the hydroxide from water. Again, you need to remember that the fluoride ion, the sulfate ion, and the nitrate ion are rarely discharged from solution. Okay, so let's move on. Let's start with the electrolysis of dilute sulfuric acid as an example. Now, dilute sulfuric acid contains three ions. We have the hydrogen ions and the hydroxide ions. You'll understand the hydroxide ions coming from water. The hydrogen ions are coming from the dilute sulfuric acid and from the water. And then the sulfate ions are coming from the sulfuric acid itself. Now, the H+ ions move to the cathode. Now, in this case, there is no competition because we only have one type of ion, the H+ ions. They are going to be discharged and hydrogen gas is formed. What do we observe? At the cathode, we are going to observe, number one, bubbles, you can say effervescence, and we are going to see a colorless gas. So we are going to observe bubbles of a colorless gas or effervescence of a colorless gas. When we go to the other side, the anode, your anions, both of them, will move towards the anode. When they get there, there's going to be competition between the hydroxide ion and the sulfate ion. Now, you remember that I've just said the sulfate ions are rarely discharged from aqueous solution. So the competition is going to be won by the hydroxide ions, and they are going to be discharged. Water and oxygen are formed. So what do we observe? We are going to observe bubbles of a colorless gas, or if you want, effervescence of a colorless gas. Now, electrolysis of dilute sulfuric acid is referred to as the electrolysis of water because the sulfuric acid part is not decomposed. Only water breaks down. So in this case, the dilute sulfuric acid can be taken as a substance added to the water to improve its conductivity, but water is the substance that's going to break down. So what happens to the solution? The acid solution is simply going to become more concentrated. Now, let us look at the electrode reactions that are taking place. At the cathode, the H+ ions receive electrons to form hydrogen. Now, to balance our equation, because hydrogen is diatomic, we are going to need two H+ ions. Each one receives an electron. Therefore, we have the two electrons, and we form our hydrogen as shown in the equation. At the anode, the OH- is going to form water and oxygen and give away 4 electrons. Now, the reaction at the anode has to be memorized. This is one equation that you have to memorize. There is no way of coming up with the correct equation in the exam. The hydrogen ion 1 is fairly straightforward, but for the hydroxide, you do very well if you memorize this equation. Now, let's go back to the cathode. When we come to the cathode, you realize the H+ ions are receiving 2 electrons. This is a reduction reaction. And at the anode, we are having an oxidation reaction because electrons are lost. Now, let's look at another example. We want to look at the electrolysis of hydrochloric acid. Now, hydrochloric acid solution contains 3 ions. We have the hydrogen ions, the hydroxide ions, and the chloride ions. The hydrogen ions move to the cathode. Again, as before, they would be discharged and we form bubbles of a colorless gas, and our gas here is hydrogen. Now, the anions move to the anode. Here, there is competition. Now, who is going to win the competition, the hydroxide or the chloride? The competition is going to be won by the ion, basically, that is present in higher concentration. When it comes to reactivity, the hydroxide and the chloride are not very far from each other. So in questions, they'll specify whether it's concentrated hydrochloric acid or it's dilute hydrochloric acid. If we have concentrated hydrochloric acid, the chloride ions are preferentially discharged and green chlorine gas is formed. So what do we observe at the anode? We are going to observe bubbles of green gas. When the substance is dilute, as a general rule of thumb, we say the hydroxide ions are discharged and the colorless gas is formed. The gas formed is oxygen, and we need to remember that water is also formed. Now, I want to muddy the water a little bit when we come to dilute. The problem we have here with dilute is that we have so wide range of values that can be considered dilute. And you need to understand that we can form a mixture of chlorine gas and oxygen gas at the anode whenever they say dilute. Okay, let's look at the electrolysis of aqueous sodium chloride. They have reaction equations. So at the cathode, we have seen this reaction before. The hydrogen ions receive electrons, and then we get hydrogen. At the anode, we have two scenarios, one for concentrated and another for dilute. Now, for concentrated, as we have said, is the chloride ions that are discharged. Therefore, we are going to form Cl2, and 2 electrons are going to be lost, an oxidation reaction. When it's dilute, we are just taking the standard form where the hydroxide is discharged, and then we form water, oxygen, and electrons are lost. Let's move on to another example. We want to look at electrolysis of aqueous sodium chloride. Now, sodium chloride contains 4 ions. We have sodium ions, hydrogen ions, hydroxide ions, and chloride ions. Hydrogen ions and hydroxide ions are coming from the water. Sodium ions and the chloride ions are coming from the sodium hydroxide. So all 4 ions are in solution. The cations, both of them, the sodium ions and the hydrogen ions, move to the cathode. There's going to be competition that is won by the H+ ions. Remember, we said sodium ions are very stable and are never discharged from aqueous solution. So we get H+ ions being discharged. We form a colorless gas. We've spoken about the observations, effervescence, or bubbles of a colorless gas. Anions move to the anode where there is competition. Now, the competition here is exactly identical to the one we have discussed before. When concentrated, chloride ions are discharged and green chlorine gas is formed at the anode. Or when the solution is dilute, hydroxide ions are discharged and the colorless oxygen gas is formed. Like I've said before, we can have a mixture depending on how dilute the dilute sodium chloride solution is. Now let's look at the electrode reactions. At the cathode, this is now becoming a very popular reaction. The hydrogen ions receive 2 electrons and form hydrogen. And at the anode, the 2 scenarios that we've discussed before, number 1, the chloride form chlorine, 2 electrons are lost, or we have the hydroxide one giving us water and oxygen. Now let's go on to another example. We're looking at electrolysis of aqueous copper 2 sulfate. Now for this one, we are going to look at 2 scenarios. The first one is the one that uses inert electrodes. Now the common inert electrodes that are used would be carbon or graphite or platinum. Now copper 2 sulfate solution has 4 ions. We have copper ions, hydrogen, hydroxide, and the sulfate ions. The cations move to the cathode where there is competition. So the competition is between copper ions and hydrogen ions. If you go to your reactivity series, you realize that the copper ions are more reactive, and therefore copper ions are discharged, and a red-brown solid is formed at the cathode. Now, what do we observe in this reaction? First of all, we have a red-brown solid formed, can coat the carbon electrode. But another important observation is that the pale blue color of the solution fades, or you can say the solution becomes colorless. When we go to the anode, the anions move there, and there is competition. This competition is won by the hydroxide ions that are discharged, and then we form the colorless oxygen gas. Water is also formed. Now, why is it that the hydroxide wins this competition? We have explained this before. The sulfate ion is very stable and rarely discharged from aqueous solution. Let's look at the electrode half reaction equations. Okay, so we start at the cathode. The copper 2 plus ions receive 2 electrons and form copper. You need to remember that this is a reduction reaction because electrons are gained. At the anode, the hydroxide ions will form water, oxygen, and lose 4 electrons. And this is an oxidation reaction. Let's look at the second scenario where we are using reactive electrodes. In this case, we use copper electrons. Now, as we have mentioned before, copper 2 sulfate solution has 4 ions, and they are copper ions, hydrogen ions, hydroxide ions, and the sulfate ions. The cut ions will move to the cathode. There's a competition there, and we have realized already that it is copper that wins the competition, and copper 2 plus ions are discharged. Red-brown copper solid is formed. When we go to the other side, the hydroxide ions and the sulfate ions move to the anode, but none of these ions is discharged. Instead, the copper of the anode, the metal itself, is oxidized to copper 2 plus ions and goes into solution. This means that the anode dissolves. So for the electrolysis, where we are using copper electrodes, the color of the solution remains the same. It does not fade. Why? Because for every copper 2 plus ion that is deposited at the cathode, another one dissolves from the anode and goes into solution. So the major observation here is that the anode becomes smaller and smaller while the cathode becomes bigger and bigger. When you look at this electrolysis, we are essentially saying that this process is used to transfer copper from the anode to the cathode, and the electrolyte itself remains unchanged. Now let's look at the electrode reactions. At the cathode, copper 2 plus ions receive 2 electrons, and then we form copper that is deposited. At the anode, the copper dissolves into solution, which means it's going to form copper 2 plus ions and 2 electrons. Now, when you look at these 2 reactions taking place, you realize that they are opposite of each other. At the cathode, copper ions receive 2 electrons and form copper. At the anode, copper loses 2 electrons and forms copper 2 plus ions. Okay, so basically that's just about it. Thank you so much.